Let's take a look at the masses here. All right, this is from your book. Here we have the hydrogen 1. Here we have hydrogen 2. Hydrogen 2, this is one of the few isotopes that have a special name. What's the name for hydrogen 2? Deuterium. And then there's hydrogen 3, but hydrogen 3 is not listed here. Do you know why? Well, hydrogen 3 is radioactive, so radioactive isotopes we don't usually list on. These are the naturally occurring. Now, how do they know that in nature, greater than 99.9% of the hydrogen found in nature is hydrogen 1? Do you know how they determined that? They determined that from the mass spectrometer. Because what happens is when you feed hydrogen into the mass spectrometer, we end up getting two peaks. We get one peak here, which would be a huge peak, and that peak would occur close to 1 U. Not exactly 1 U. It occurred at 1.007825031 U. Now, is that an exact number? No, it's just a measured number. The only exact number is carbon 12, which we see here. So we have a huge peak here, which would be 99.9885% of the area of the peak, or the height of the peak. And then we get a tiny peak, a second peak, and there'd be no other peaks. So we run hydrogen because tritium's so rare in nature. And so the second peak would come at about twice the mass, 2.014101778 U. And then it would account for a relatively small percentage of the total peak area. And so those would be the two peaks. And so how do we know? We measure it, we observe it experimentally, and then you just kind of memorize it. But we want to get away from memorization. We want to be able to predict these things. And so how could you predict that? Well, maybe we could see a pattern here. So for example, here's hydrogen. If we look at helium, how many do you see for helium? 2. These are two isotopes. One is helium-3, the other is helium-4. Now this number below here represents the element number. And so when we look at the periodic table, the element numbers are red. And the element numbers coincide with the number of protons. So all hydrogens have 1 proton. So if you see the one, we call that the atomic number Z. All helium atoms have 2 protons. So it's 2. So this number down below is not necessary because that's just the number off the periodic table. We can find that out. But helium is 2. Then we go to beryllium. Beryllium, look at 100% of all beryllium atoms are beryllium-9. There are no other isotopes. And so if we ran beryllium through the mass spectrometer, we only end up with 1 peak, no other peaks in the mass spectrum. Now, it would be nice to be able to predict this stuff, but, this is not really the realm of chemistry. Chemists, yeah, it's interesting to know, but are the chemical properties different between the hydrogen isotopes? No. And chemists are interested in chemical properties. Now, if the chemical properties were impacted, yeah, then we would care. But, do you see much isotopic fractionation in the beaker in the lab? Is the bottom of the beaker more enriched in the heavier water molecules than the top of the beaker in the light? No. We'd need a huge column of water to see that kind of fractionation. Are chemists really into that? No, not that much. Geologists, yeah, they're interested in that because they want to see where it formed, where things form, that type of stuff. And so this type of stuff doesn't really have a huge impact on chemistry. This is the realm of what we call nuclear physicists or nuclear chemists. Nuclear physicists and nuclear chemists are very interested in the nucleus in particular, but in atoms, and they want to predict, how many isotopes and the stability of those isotopes and that kind of stuff. But for us, this is just just factual knowledge, just doing some measurements and running it. And so, for example, for carbon, there's carbon 12, there's carbon 13, and there's carbon 14. Carbon 14 is radioactive. For nitrogen, there's nitrogen 14, nitrogen 15. For oxygen, there's 16, 17, and 18. If you look at the mass of oxygen 18, it's close. It's 17.9991604 U, very close to 18. You look at the mass of oxygen 16 is very close to 16 here. But 99.757% of the oxygen you consume is oxygen 16. And so when you're breathing in air, we don't breathe in that much oxygen 17, nor do we breathe in that much oxygen 18. It's mostly oxygen 16.
If you go to higher and higher elevations, maybe at the top of Everest, you'd see a difference. You'd be breathing probably more and less, more 16, less 17 and 18.
Then we continue on. These are just from experimental facts, just experimental observations. So there's fluorine, this lighting in the afternoon is not good. Anyway, this is a table in your book you can take a look at. So we can see the isotopes and their weights, how much they weigh, and how are these masses determined again? What instrument do they use to determine the mass of the atom? The mass spectrometer. And if you know, like, just roughly how it works, then you're okay. But you don't really need to know that. All right, then what we want to just start doing is we want to start looking deeper into this. Okay. So we know how much they weigh, but based on their weight, are they really going to tell us how they react chemically? Maybe for density, it will make a difference. Like deuterated water is going to be more dense than normal water, and that type of stuff. But as far as trying to predict how things behave chemically, like chemical properties, chemical reactions, then it doesn't really tell us much. And so first, we'll just nail down the composition a little bit more. With the composition, let me talk about the composition of isotopes. We look at the nuclear symbol to tell us the composition. The nuclear symbol is going to just be the elemental symbol, which is going to be one or two letters. For example, neon would be capital N, lowercase e. Then we have a Z. This Z is optional. I don't usually write Z down here, but it's optional because this is just the number of the element. So neon's element number 10, and so Z would be 10 here. And then we have A here. A, we need A. And so what A is called the mass number. The mass number is not a mass. The mass number is not a mass. It's close to a mass. The mass number is the number of protons plus the number of neutrons. And so, for example, neon 10 would have a mass number of 10. It's close. The mass is close to 10U, but it's not exactly 10U. We can figure out what its mass is. It's closer to 9.99 something U. But that means how many sig figs are in 10 here? How many sig figs would you say are in 10? 2? Normally you'd say 2. So that means it can vary anywhere from about 9.6 to about 10.4. And so we'd have 9.6. We might overshoot or undershoot, the number of protons or the number of neutrons by half. Can you have half a neutron or half a proton? You can't. It doesn't exist. It break up into smaller particles, and the smaller particles would be like quarks and that kind of stuff. But this is infinite sig figs, we'd say. We can't have a fraction of a proton or a fraction of a neutron. It's just not possible. We'd have to have whole numbers of those. Whereas the mass of neon is different. The mass of neon, let's see, I don't have it here, but we could look it up, and it's like 9.99. All right, so from this we can get the composition, but it's still not enough. So we got to look for more. And so let's go to this and just kind of go through a presentation from the book's perspective. So I veered away from the PowerPoint, so now I'm going to come back to the PowerPoint here, but we're looking at atomic theory part 1. And one, automatically I'm assuming everybody believes in atoms, but you don't necessarily have to believe in atoms. Somebody should prove to you that the atoms do indeed exist. So if a friend asks you, they don't believe in atoms, they need some hard evidence for atoms. Could you supply them with some hard evidence that atoms exist? Yeah. But if you think back in Dalton's time it's very difficult, because they didn't have the sophisticated instruments we have today. The instruments we have today, like the mass spectrometer, we can weigh single atoms, and other instruments we can do different things with. In fact, people have visualized single atoms by making them glow. I think I showed that earlier. But in Dalton's time, Dalton came up with the first meaningful atomic theory. And I guess it said the Greeks came up with the idea of atoms, but the Greeks, when they were thinking of atoms, all the atoms were the same. They were just put together differently. Dalton came up with a different idea. He thought of, certain elements have different atoms, and so there are going to be different types of atoms, not just how they're put together. And so these are the basic features of Dalton's atomic theory. An element is made up of atoms. All atoms of a given element are identical. Is that true? All atoms of a given element are identical? It's not true. I mean, hydrogen, there are 3 types of atoms. H1, deuterium, and tritium. It's not true. But Dalton didn't know about that. Dalton didn't know about what? The existence of isotopes. Why? It makes sense he didn't know, because can you taste the difference between a hydrogen 1 and a hydrogen 2? You can. And so it makes sense he missed that. So the theory's been modified a little bit. Theories, they can change over time, and this one did. Atoms cannot be created or destroyed. Okay, that's true for chemists, because chemists deal with chemical reactions. In chemical reactions, the atoms are just rearranged. Atoms are neither created nor destroyed. That's conservation of mass. But for nuclear chemists, it's not true. Like tritium, tritium will decompose into other stuff. And the same thing with other radioactive atoms, like uranium. Uranium doesn't stick around. Uranium decomposes. In fact, chemists tried to do this. Chemists tried to transmutate from one element to another element. In fact, chemists were trying to make lead into gold. Those were the alchemists. But unfortunately, you can't do that with chemical reactions. Chemical reactions don't mess with the number of protons in the atom. And so that doesn't happen in chemistry. However, nuclear chemists, it can happen. Like all these elements here were man-made, from called the transuranium elements, man-made elements. And so elements have been created. They've been created from smaller atoms, of course, bigger atoms from smaller atoms, vice versa. But this is okay for chemists. Okay, the next one. All atoms of any given element have the same properties, including mass. Well, they have the same properties, excluding mass. Mass doesn't have to. But for some, like beryllium only has 1 mass. So all atoms of beryllium have the same mass. But even if they have different masses, what the common feature is they have the same number of protons, which gives them, there's got to be a connection between the number of protons and the way they behave. Atoms of different elements have different masses. Yeah, is the mass really the important critical factor there? Just because something weighs more or weighs less, is that really going to dictate how it behaves? No. The critical factor, and this is something Dalton didn't know because he didn't know about subatomic particles and that kind of stuff. Atoms of different elements have different number of protons. Therefore, their behavior is different. Now, what's the connection between protons and behavior? Well, we got to find that out. We don't know just yet because we haven't really gotten into it. Atoms of different elements may combine in ratios of small whole numbers to form compounds. That's true. I mean, this would be like CO2, carbon dioxide. This would be like CO, carbon monoxide. So we have that. So those are the basic features of Dalton's atomic theory. We can see it listed here. This list of 5 point. Each element is made up of individual particles called atoms. Atoms are indivisible. If you try to break up let's say a carbon-12 atom, it's no longer carbon-12. It's protons, neutrons, electrons. All atoms of one element are identical in every respect. Well, that's not true anymore. Atoms of one element are different from atoms of any other element. That is true. atoms of one element combine with atoms of other elements to form chemical compounds. That's true. Well, during Dalton's times, there were plenty of people that didn't believe in atoms. There's some people who thought matter can be broken down into infinitesimally small pieces. And therefore, if you have a sample of carbon-12, you can just keep breaking it into smaller and smaller pieces of carbon. And there's no limit. And so, how did he convince those people? You know how he convinced those people? For Dalton, what's the proof? What proof did Dalton have that atoms exist? And there were plenty of people who were skeptical of this whole idea of atoms, but what proof did Dalton have? You know the proof that Dalton had? The proof that Dalton had was, what do theories do? Theories offer a fundamental explanation. A fundamental explanation of what? And so when we look at the development of theory, it starts off with observation. And where did atomic theory come from? What observation did atomic theory originate from or arise from? The development of Dalton's atomic theory came from the observation of mass. In fact, a conservation of mass. That is, when you have a chemical reaction, if we have some kind of reaction or process, then the mass before and after are the same. Mass before and after are the same. And so we have conservation of mass. The conservation of mass led to the law of conservation of mass. Basically it's a pattern. And this pattern kept repeating over and over. And since the pattern just kept repeating over and over, they made it into a law of conservation of mass. And what Dalton hypothesized is that when you have a chemical reaction, the atoms just get rearranged. The atoms don't disappear, you don't make new ones. You have all the same atoms that you had before, they're just rearranged. And so the hypothesis here was the atoms. And that led to the theory, which is atomic theory. And so what proof did Dalton have? What proof did Dalton have? Dalton had the proof of the conservation of mass, but is that really good proof for the existence of atoms? Conservation of mass? No, you would think you'd want something a little bit more, right? And that little bit more came from here, because hypothesis is tentative, fundamental description of what's happening. A tentative because it doesn't have widespread acceptance. When something gains widespread acceptance, then we call it a theory. And so atomic theory had gained widespread acceptance, not just because of this, not just because of it was a pretty good way to visualize what's happening in a reaction. When you visualize it as atoms just being rearranged and the same atoms are there before and after, then it's easy to visualize. And so it's a good fundamental description of the conservation of mass. But theories not only have to provide a fundamental description, but theories also have to do what? Theories also have to predict new, unforeseen results. And so what did Dalton's theory predict? Dalton's theory predicted the law of multiple proportions. The law of multiple proportions. And what the law of multiple proportions says is this, when two elements combine to form more than one compound, they combine in simple whole number ratios. So for example, 1 to 1 or 1 to 2, CO2, H2O, right? But if mass That is, if elements were infinitely divisible, then they can have any amount. Then, for example, can you have water with a little bit less hydrogen? Let's say, I'd like some water with a little bit less hydrogen. Maybe it tastes better. What's that? Well, I'm talking about water. Like water having like a little bit less hydrogen would be H1.90. Can you have part of an atom? No. But if matter were truly infinitely divisible, then what's keeping it from combining in any ratio it wants? You could have a little bit less, a little bit more of whatever element you want. Instead, we have simple whole number ratios. We don't have a whole bunch of different compounds. We have carbon, carbon monoxide, carbon dioxide, right? We don't have carbon 2.1, oxygen 3.5, those types of things. These simple whole number, and so this pretty much gave it much more widespread acceptance. Even though if you're thinking about proof, conservation of mass, that's one piece, but the more proof that you can have, or the more evidence that you can have supporting your theory, the better. So this was pretty good, even though people have never visualized atoms in the 1800s here. There's a lot more version. Then we talked about the electron here. The electron, the discovery was credited to J.J. Thomson. What was the instrument he used? CRT. So that's pretty much what you need to know. The electron is a very light particle. It's about 2,000 times lighter, actually 1,837 times lighter. Okay, now what we think, now we got the composition, but how are things arranged in the atom? And so we know what the atom's made up of. It's made up of protons, neutrons, electrons. How things are arranged in the atom, there are two competing hypotheses. One hypothesis was a plum pudding model. In the plum pudding model, the electrons are like the plums, and the protons are like the pudding. And the pudding's spread out as a gel. And so these are negatively charged electron particles are embedded within a positively charged spherical gel. And so things are kind of spread out and evenly distributed. And so it's fairly homogeneous. The other hypothesis was that things weren't homogeneous. Things were very heterogeneous. In other words, the atom's like this. In the center of the atom, we have a nucleus. And within the nucleus are the protons and neutrons. Outside the nucleus is mostly empty space in which the electrons are dispersed here. And so which model won out? The model that won out is the nuclear atom model. So the critical experiment here was the Rutherford scattering experiment. So this is where a hypothesis was tested and an experiment was conducted and showed that this model is the correct model. And in the Rutherford scattering experiment, they put a radioactive element in here. That radioactive element broke down. A chunk of the atom breaks off. The chunk of the atom that breaks off is called an alpha particle. And so there are a whole bunch of atoms in here. So atoms are losing a chunk of it and shooting out alpha particles. These alpha particles consist of 2 protons and 2 neutrons, so they have a positive charge. And so the alpha particles get shot out of this, and there are slits here, so it creates a beam, so like 2 slits. So only the particles moving like this will be emitted, and the other particles will bounce back inside here. And so we get a beam of alpha particles shooting out of here. And then they have a very thin piece of gold foil. They're showing the gold foil here blown out. This gold foil is only 2 atoms thick. So very, very thin in this case. What happens with most of the alpha particles is they go straight through undeflected. They go straight through undeflected because it's mostly empty space. Sometimes they'll interact with electrons and be slightly deflected. Sometimes they'll interact with nucleus and be slightly deflected. And so in the plum pudding model, this would be it. A lot of these would go straight through. Some would be slightly deflected. But the difference here is in the nuclear atom model, if there's a direct hit, then we have a positive alpha particle hitting the positive nucleus. There's going to be tremendous electrical repulsion, so positive repulsion, which is going to repel that alpha particle back. And so we wouldn't see this kind of deflection in the plum pudding model because things are spread out more evenly rather than concentrated here. And so because of these
scattered alpha particles at a very high angle. This is what led to proof of the nuclear atom model. And so this is the general structure of the atom. The electrons out here in empty space, a nucleus that contains the protons and neutrons. You can blow that up a little bit and take a look at the atom here. And so here we have the atom. The atom is approximately 10 to the minus 10 meters. Did you hear 10 to the minus 10 meters before? 10 to the minus 10 meters is called an angstrom. And that's the definition of an angstrom. So 10 to the minus 10 meters, an angstrom. And so the atom is approximately 1 angstrom in diameter. That's a hydrogen atom. Some of the bigger atoms will have larger diameters, so it can go up like 1 to 6 angstroms in diameter, the atom is. An angstrom can be related to picometer. This would be equivalent to 100 picometers to 600 picometers in diameter. And so we'd either use angstroms or picometers as a convenient measure of atomic diameters and atomic radii. The nucleus, that's the region occupied by the electrons, most of the atom, but the nucleus here is occupied by the protons and neutrons. Now this is just a sketch of what it might look like, but how the protons and neutrons are arranged in the nucleus is not really something that chemists really worry about. Who worries about that the nuclear chemists and the particle physicists. They're very interested in how this is arranged. And they're very interested in predicting, how many isotopes and whatnot. But, all we know is it's a tiny nucleus. The tiny nucleus is, if the nucleus were 1 centimeter, then the atom would be 100 meters in size. So it gives you just an approximation. There. And so when we look at the nuclear model of the atom, every atom contains a small and extremely dense nucleus. If an atom is mostly empty space, let's take a look at gold, for example. Gold consists mainly of empty space, but gold is one of the most dense elements there are. Do you know what the density of gold is? About 20 grams per cubic centimeter, or 20 grams per milliliter. But if you look at gold, there's a lot of empty space. This empty space, and then you see the gaps between the atoms here? That's empty space. And so this whole thing would have a density of about 20 grams per cubic centimeter. But if you just take the nucleus of the gold atom and then figure out the density of the nucleus alone, do you know what the density of the nucleus alone is? If you only have the nucleus and you had just a volatile pure nuclei, then the density would approach 20 tons per cubic centimeter. So it's just a horrendous, incomprehensible number. 20 tons packed into a cubic centimeter, or 2 tons, I forgot the exact number, but it's enormous. And so we're looking at tons per cubic centimeter versus grams per cubic centimeter when we're looking at gold. How late do we go till today? 30? Or 35? 30? All right, we have a minute. So then we talked about the protons, neutrons, and electrons. We talked about the isotopes. We talked about characterizing isotopes. So I just want to finish with one row of this. Here are a couple of, we can finish this table pretty quick. And so if we look at barium, we have the element, what's the elemental symbol for barium? Ba. The atomic number of barium, so what number element is barium? So we look on the periodic table, barium is element number 56. Okay, the atomic number is the number of protons. Atomic number Z is 56. We'll have 56 protons. Now how many neutrons do we have? Well, the number of neutrons depends on the mass number. This is barium 138. And so 56 protons plus how many neutrons gives us 138? 82.
And so the number of neutrons would be 82. The mass number is this number, would be 138. And the name of the isotope would be called barium-138.
C.
And then let's do one more here. Oxygen, elemental symbol, O. Atomic number, 8. Oxygen is element number 8, which means how many protons? 8. Remember the protons. Number of protons dictates the chemical properties. And then neutrons, 10 neutrons. So that means the mass number will be 18. Is that the 2 sig figs or? Infinite. Yeah. We aren't going to have part of a proton and part of a neutron. And so the nuclear symbol, now, oxygen already automatically is element number 8. So if you leave off this 8, which most people do, then it's just oxygen 16, which is written like this. The 8 is a little bit redundant. We don't really need it. So we're looking at oxygen 16, like this. And the name, oxygen-16. All right, we'll stop here and then we'll continue.